So Josep Miquel, go
Yes.
ahead. And yes, go
Yes,
ahead.
okay. First of all, I want to apologize for two things. First, if there are any cosmology, I think the title, you will know that's not appropriate. I mean, even with the word of nano, that's far away to be in a nano big bang. Yes, it was a bomb. I'm going to talk about an explosion, a bomb with a lot of energy involved, but of course, it's nothing compared with the Big Bang. Just was a bit of marketing. The second is this is a last minute presentation. So just prepare because today we were supposed to have Alice Thur, but she is pregnant in the 8th month and she didn't feel well enough to have her presentation. So I decided to go ahead. And because I just published, was part of a publication this year related with this issue of the Orion explosion, I thought that was maybe interesting for the people at the ICE to show these new results. Okay, so here you see in the first slide, you can see Orion constellation. Okay, I show you that because it's surprising that when you ask students, even in the master, and you show a picture of the Orion constellation and you ask them, do you know what is that? Not everybody knows what Orion looks like, and it's probably the easiest constellation in the sky to figure out. Okay, so this is a constellation where we basically, the importance of Orion is we have the nearby, the more nearest giant molecular cloud forming high mass stars. So it's a very good place to study how massive stars form. Okay, so let's move. Okay, so before I present Orion and all the properties of Orion, let me make a brief introduction of what we know in a brief of how star formation proceeds. And we start with an idealized case of isolated star formation for a low mass case, because this is very well known, characterized. And we know from the observational facts, which are the signposts. So we start with a dense core of gas and dust. And once the density and the length scale reaches some value, self-gravitation will start to contract, right? And when the gravity starts to energetically overgo over the pressure terms from thermal pressure, gravity, magnetic field pressure, or the turbulence, then you start to contract the core, and you will form a protostar at the center. And that, I mean, the contraction initially is isothermal, or nearly isothermal, basically because of the cooling of the gas. But at some point, because you become so dense that the dust particles become optically thick, and that once that happens at the center of the core, the temperature increases very fast, and you start to dissociate first the molecular gas, and then even sublimate the dust when the temperature goes over thousands of kelvins, and then you form a protostar at the center, a very dense and hot protostar. And the protostar can last until it goes to the main sequence for a low mass for several millions of years. In the initial phases, of course, you have the protostar surrounded by the dense envelope that is contracting, and because you have some angular momentum, the angular momentum that will produce the formation of an accretion disk around the protostar. Okay, and for low mass, we know now that this accretion disk, we can call it planet-forming disks. Okay, because now there are strong evidence that even in the protostellar phase, you start to put the seeds of planet formation. Okay, and because you also have angular momentum, you have some excess of angular momentum, but you have also gas and dust, especially the small dust particles that are attached to the magnetic field, are coupled to the magnetic field. So the tension between the magnetic field due to the rotation, that's going to create or generate a strong interstellar jets, bipolar outflows at the scales of launch at scales of few AUs. Okay, and this is a very well known observational signature. So when you see a protostar, you usually see these bipolar, very highly collimated, very fast bipolar jets traveling at velocities of a few hundred kilometers per second. Okay, so this is a strong observational signature of star formation. Okay, and this is relevant from what I'm going to say before later on. After this keeps evolving, most of the gas in the envelope will fall into the disk and then into the star, making the star to grow. And at the end, you will the envelope will just accrete or dissipate because of these outflows, and you will form like the star planet forming disk system, and this is what we call usually the class 2, class 3, the theta wave phase, where you still have outflow bipolar jets because you still have accretion of as long as you have accretion from the disk to the star, you will have these bipolar jets. Okay, and at the end, this planet forming disk will form a planet system. Okay, so this is for the low mass. For the high mass, there are two possibilities. You can form also high mass in the same scenario of low mass. The only thing is because they are much more luminous and massive, you will start the fusion process when they are still in the protostellar phase, when still are surrounded by a lot of gas and dust, and that will create the UV radiation that will produce the star, will start to destroy the dense molecular gas and produce an H2 region. Okay. The other scenario is because high mass stars don't form isolated, but they also form in big clouds. So you can have fragmentation and form clusters, and you have a strong gravitational potential. You may have mergers, right? Or at least a concentration of stars or protostars at the center of the densest parts of the clouds. Okay. Okay. So now, after this short introduction, let's start about first giving some hints of the Orion giant molecular cloud. The giant molecular clouds are clouds of tens of parsecs, masses between 10 to the 5 up to 10 to the 6 solar masses. So they are very massive. And these are the places where we know the massive stars, the OB stars, are formed. Okay. And the closest one to the solar system is Orion. Orion is only at a distance of only 400 parsecs. Okay. So it's quite close to us. Okay. The total molecular cloud has about 10 to the 5 solar masses, so it's very massive. Here in the picture, here you have the Orion Constellation, and in the red, the red color, it shows you the location of the CO molecular emission. That the CO is a very good tracer of the cloud, okay, because it's very abundant and the chemically is very stable. So it's really at a large scale is probably the best tracer with us to trace these clouds. And you can see basically when now because now we're in summer, when we go to the fall, if you look at Orion, you have to think about this picture. Okay, you will you have the three Marias here, you have here the Orion Nebula, and you have and every time you look at Orion, you have to think that there is a huge amount of molecular gas in the constellation. Okay, and you have two main bright clouds, Orion B and Orion A, and more or less in terms of molecular gas, they have more or less the same amount. Okay, of course, as I said before, these are sites of high star formation, and we know there are of the order of 20 massive stars of OB stars already formed in this cloud, and in dots, in the green dots, show you the location of the young stellar objects, so from both the massive ones and the low mass. And this has been possible thanks to Herschel and Espacials because they are in the infrared, they are very sensitive to the hot dust heated by the young stars. And you can see here clearly the location of Orion B. The location is localized in some regions of the cloud and mostly are clustered. Okay, and in Orion A, difference with the Orion B is you see stars being formed all along the big filament, although there is a big concentration of young star objects around what we call the Orion Nebula, and I'm going to show now a picture of the Orion Nebula. Of these 4,000 young stellar objects, about 300 are protostars. And when I say protostars, I mean young stars that are surrounded still by a lot of mass and of interstellar mass of gas and dust, and with a mass similar to the star. Okay, so still there's a lot of reservoir to make grow the star. Okay, and because you see it's less than 10%, that means that dynamical time scales of the low mass of the protostars is shorter of the full young stellar objects time scales. Okay, so now I'm going to. Oh, this is a Herschel image. The Herschel was an infrared telescope, basically mostly in the mid and far infrared. In the blue image, basically is the cold dust. This is the filters at the longest wavelengths in the far infrared. So basically, you're seeing the dust composition, the dust location of the cloud for the cold dust. So you can see it's all over the cloud, and you see these kind of intricate filament structures. Okay, and the other one, the yellow one, this shows the dust, the hot dust that you can see is more or less localized around the Orion Nebula, and this is because this is dust heated by the massive stars. So now let's look at the Orion Nebula. Okay, as I said before, this is ongoing formation for massive stars. This is a very nice picture of a Hubble telescope. That's what I wanted to show you. And well, here you see dark spots. Dark spots is very dense and cold gas and dust that is in the foreground, and because of the dust, it blocks the radiation from behind from the bright nebula. The bright nebula is basically scattered and ionized gas, scattered by small dust particles, and this is radiation coming from the massive stars. Here you can see some massive stars that are blue. They are the blue ones. These are some of the massive stars. Now we're going to zoom in this region. Okay, which is what is called the Orion BNKL nebula. BN is Becklin, Neubauer, and KL is Kleiman Low, and these are the publications where they basically is the first zoom in of the regions. This is a very complex region, and you can see again in this Hubble telescope. And just want to highlight three zones in this of the BNKL region. First, you see these kind of reddish stars. These are the trapezium cluster. These are four massive stars of the order with masses of between 15 and 30 solar masses. Two of them are eclipsing binaries, and then you see this kind of bar. This is the Orion bar, and what we are seeing here is the surface of the cloud that is being exposed by the UV radiation from the trapezium cluster, and this is a very interesting place to study astrochemistry. It's astrochemical lab because the UV radiation drives a lot of chemical reactions, and you have a very interesting chemical features there that can be studied. Okay, but now we're going to focus on the region here that in this picture you see nothing, looks boring, but when you go to different filters, and that includes near infrared, you see completely something very different. Okay, this is from the Subaru telescope. In the near infrared, you have the J, K, and the H, the K band and the H2 narrow filter. The H2 is the molecular hydrogen, vibrationally excited lines, and these lines can be excited through chokes. So basically, it's an interstellar choke tracer. Okay, and this is in red. So you can see here a lot of molecular hydrogen choke excited. And when you see here, you can see here this very complex morphology of kind of bow shocks. Now I'm going to show an image with more detail. So something very violent is going on at the center of this region. And here is where you have these trapezium stars, but the present formation of massive stars is located here. And this is because you have much more dust and gas reservoirs to form this star. So in the 90s, there was a lot of discussion of what these kind of features were tracing, right? And this is an old image in the near infrared where you see this kind of filaments. And I'm going to go to the next slide. Here you can see very more clearly. This is the molecular hydrogen. And you can see this kind of fingers. Let me just here. Oh, sorry. Okay. Let me see. Draw. Okay. Let me see. Okay, so here you see these kind of, well, we call it the Orion fingers, okay? And you see everywhere, in all directions. Now, almost not completely isotropical, because you see basically one here, and then one conical thing here, and you have many of them, okay? And if you just take one of them, for example, this one, this resembles a lot what you see in isolated star formation of low mass or intermediate mass, or even high mass when they are relatively isolated. The feature here is you see a very complex network. So what's going on here? This is not the standard bipolar outflow. So in a bipolar outflow, you have the start, you have a bow shock here, right, of the gas going in this direction, and you have the other direction, the other bow shock. And you may have two other sources, one here, another protostar here, 2, 3, 4, but nothing like that. Because in order to explain this is very difficult to explain. Okay? Like it's not possible. The amount of young stars here in the center of the core is not enough to have any of them. So you have too many, right? So something is going on which is not standard. It's not canonical star formation. These are not the typical bipolar outflow launch at the US scales in a accretion disk. Okay, something going on is going on here. Okay, all these fingers have velocities very high, of the order of a few hundred kilometers per second, and the total energy only in these fingers is of the order of 10 to the 47 Earths. So it's a lot of energy here. Okay, and we have a collimation factor that is very poor, because as I said before, the opening angle is 200. So something is going on that is not the standard way of star formation. Okay, when you go to the CO, because CO is also a very good tracer of bipolar outflows, molecular outflow being swept up by the winds coming from the inner part of the disk, and you see very clear bipolar outflows. When you look at this tracer CO for Orion, you see something that is very messy. It's not. It has kind of a bipolar morphology, but it's very, very, again, with a very wide opening angle that is not well predicted from the observations of typical outflow. Okay, so in CO also give you some idea. Okay, and also when you go to molecular dense tracer, so if you pick up now what's going on at the scales of the dense molecular Gauss that is supposed to be contracting to form massive stars. Orion Bay and BNKL region was always something particularly different from the other high mass star forming region. You have this very rich chemistry of molecular lines in the millimeter and submillimeter, and this is just due because you have the dust and the gas is a very high temperature of the order of 100 kelvins. This evaporates the ices, and the high temperature and densities allows you to create complex molecules like CH3CN, methanol, formaldehyde, and even biomolecules like acetic acid, for example. But the molecular distribution of Orion was distinctive. You have the hot core that has this kind of U shape, okay, with a lot of N nitrogen-bearing molecules, and has the typical hot core kind of morphology. And you have this called molecular ridge that we studied 20 years ago, where it has some particular chemistry and some physical properties that are different from the hot cores. And we thought it's like an ambient cloud at the surface of the hot core that is being choked, and you get a lot of radiation, and that produces some molecular peculiar chemistry. But the first evidence of what's going on came out in 2005 by the Mexican radio astronomers in Morelia, by Luis Felipe Rodriguez, by observing, they have been observing with the BLA Orion for many years, over like 10, 20 time scales, and that allowed them to measure proper motions of the radio stars. In fact, there are three of the massive stars are very bright in radio, and they have very compact emission. The source BN, the source I, and source N. And they measure proper motions over 20 years period. And what they found, and these three stars are runaway radio stars, and these are massive stars, okay? And they could measure like proper motions of the order of 20 and 30 kilometers away, kilometers per second. And the direction, when you extrapolate the direction inwards, all of three stars come from the same center, which is that's the key. That's the first evidence of a dynamical interaction between three massive stars, because they have the same origin. So the circle, they give you the statistical region where you have high chances where the dynamical interaction happen. Okay. More recently, a few years ago, also with the BLA, with fainter sources, the Mexican radio astronomers, they found two more radio stars where they have proper motions, also compatible with runaway radio stars, and with the origin also coming from the center of this place where probably there was this interaction. So we have like a 5-body interaction, right? Some of them may be part of a binary that's been just disrupted by the gravitational tidal forces during the dynamical interaction. And by extrapolating with the velocity and the distance, we know that this interaction happened about 500 years ago. Okay, there is a lot of uncertainty in the age, but this of this over there. Okay, so we cannot go to the catalog history because we don't have a precise date of the explosion of the dynamical interaction. Okay, when we look at these 3 stars and the arrows are these red arrows show the direction of runaway stars, and you can see matches very well where you have this very complex network of fingers of outflows going out. Okay, so everything correlates here. You have runaway stars that come from the same origin than these fingers. Okay, so that's probably we are looking different evidential evidence of the same feature. Okay, the second evidence is from, I said before, these fingers. Okay, that the travel of velocity of 200, and they have they look like coming from the center of the Orion Nebula. But I think the most clear example was coming from the millimeter observations by another Mexican, with Zapata. We observed with the submillimeter array, they observed the CO emission from the molecular outflow. I mean, the molecular hydrogen traces hot, dense gas being shocked, and CO traces the coldest parts of this outflow. And what he did was something very, very clever, because the CO maps looks very, very messy when you look at the SMA data. But what he did is, okay, let's go channel by channel and identify the brightest clamps of each channel, because the emission is very messy. So just focus on the brightest clamp for each channel, and let's measure the location. And what he found is, for example, here at some velocity channel, that's the brighter. This is the location of the peak of the brightest clamp of this peak. Go to the next channel, and he found that, well, the next channel is here, the peak. The next channel is here. The next channel is here. And what it happens is you see these linear features. So there is a velocity gradient that is linear. And this is for another clamp. The blue is for the blue shifted emission. The red is for the shifted emission. And when you see the overall pattern of the peak of the clamps of different velocities, you see this radial pattern. Okay, if you now extrapolate toward the center, these figures, all of them point out toward the location of the interaction between the 3 stars. So now we have a strong correlation of the dynamical interaction of the 3 stars, and probably involved with more stars, with this outflow, this explosive quasi-isotropical outflow in the form of fingers. And the other interesting feature, now let's make a position velocity cut. This is the projected distance from the origin for the different clamps, and this is the velocity. This velocity here is the cloud velocity. So if you take the clamp here that picks at this velocity, you see that this clamp, as you go at different velocities, you see this kind of velocity gradient, which looks like that means the velocity is increasing at a further distance from the center. So you have kind of a Hubble flow like fingers. Okay, so you have acceleration of gas as you move away. Okay, this is a picture of combining the different tracers of these fingers, these outflow fingers. Blue is the ionized iron, so this is tracing hot gas of the order of more than 1,000 kelvins. The molecular hydrogen, that's probably tracing few hundred kelvins, and then in green and in red you have the CO. This is tracing the outflow, but from the colder component of the other few tens of kelvins. Okay, and you can see that everything is correlated, and you have very distinctive physical features. Some is very hot, some has been already cooled down, but all form part of the same system. These kind of explosive fingers that are coming from the origin center of the dynamical interaction between the stars. This is okay. Let me just go back. So what I'm going to show here is the data cube of the SMA observations. So we will cross the velocity of the data cube. So we start with the blue shifted velocities. We move increasing velocities until we go to the red shifted velocities. So at the beginning, you will see the highest blue shifted velocity, and then decreasing in velocity. At some point, you will cross the velocity of the cloud. Of course, at the cloud velocity, the emission of the CO is very extended. You will see kind of a messy emission, and then you go back to the high velocity that is coming from the fingers. Okay, and you can see the velocity gradient. Okay, and now you go to redshift, and you can see how the clamps become as the velocity increases, become farther away. Okay, and this is the final video. Okay, so you can see clearly, and this is from the propaganda from the institution from ALMA, and you can see here clearly this effect of gas being expelled down from the same origin. The third evidence comes from a lower velocity component, and this was found by using a rare isotope of the CO, the 13CO, which is more less abundant, so it traces. Basically, you need to detect it well. You need much more amount of gas, so basically it traces the densest part of the region. And what they found, again, Zapata and collaborators, what they found, the CO at the low velocities, they found that the CO is coming from a bubble, kind of as a spherical or from a spherical shell bubble that apparently has a velocity pattern that is compatible with being expanding bubble. So this is another evidence that of this explosive event. Okay. The fourth evidence comes from the properties of the hot core, and I mean, Zapata. I think it was Zapata in 2011. He published a paper titled "A Hot Core That Is Not a Hot Core." Okay, which is, I think, a cool title, and basically tells you the reality. Okay, everybody was referring to this hot core at the center of the explosion as a standard hot core, but when you look at the physical properties of the gas, you start to see that it has not anything to do with a hot core. Okay, a hot core is, as I said before, is a dense, very dense amount of molecular gas and dust that is being heated by the protons at the center. And because they are very luminous, that makes the gas a very high temperature with respect to molecular clouds. So I'm talking about 100 to 100 kelvins temperatures. Okay, and that gives you a very rich astrochemical network of lines. And this is internally heated. So usually you expect that the temperature decreases as you go out in the dense core. And this is very well tested and seen. This is a typical head core. When you look at the temperature by using different tracers with different excitation energy levels, what you see is completely something different. I mean, this is here in color scale is the CH3CN, which is a hot core tracer. And in red color, you have a vibrationally excited SO2 lines. So yeah, only the thing that is vibrationally excited, that implies that you need a high temperature to excite this transition. And then you have also an vibrationally excited H3CN, which is even higher. So this is H3CN, you have an energy level at almost 1000 Kelvin, and the SO2 a bit lower, on 600 Kelvin. And the SO2, what it looks like is tracing the surface of the hot core. And the H3CN, which is even higher temperature in order to excite the line, is coming from a smaller region, okay, close to the origin of the explosion. So this is strong indication that this hot gas has been externally heated, not internally heated. So that's why this is a hot core that is not a hot core, okay? Because it's not a massive star inside of the core that is heating the gas. That, of course, there may be some stars inside, but the main radiation that hits the gas is externally heated. And that implies an origin probably related with explosion of the dynamical, produced in the dynamical interaction of the massive stars. Okay, and this is another feature where you see that the more heated gas, basically you see a chemistry of where you have basically mostly of the complex molecules are nitrogen-bearing molecules, where in the outer layer, in the molecular ridge, is basically oxygen-bearing molecules. And this is in agreement what you expect when you have more hot gas, like in the massive hot cores, you are dominated by nitrogen-bearing, when you go to hot corinos, that these hot cores produced by low mass, where they cannot heat the gas at such higher temperatures, you basically produce more oxygen-rich molecules. Okay, and this is like, so these are temperature gradient probably because of the explosion. Okay. There's another indication in the hot core is when you see the line width, you see this kind of linear features with a high line width, a higher line width than the rest of the hot core, and they are like a radial located with respect to the origin. So that probably give you some evidence that this larger line width is because of the associated with the explosion. Probably. The fifth evidence comes from one of the sources, which is called source I, which is kind of strange name. And this is a very massive young star, 15 solar masses, and it's a unique star in the sense that for many, many years, I remember when I was a student, everybody knew source I was unique because it has SIO measures, which are not so, are very common in the circumstellar envelopes of post-AGB and stars, but not in star-forming regions. Okay, and not only that, but the SIO measures, most of them they have like a vibrationally excited SIO measures. This is also another feature of evolved stars. And some of the molecules in this source I, like SIS, is again another molecule that is usually not present in star-forming regions, but usually is the typical tracer of the circumstellar envelopes in post-AGB stars. Okay. So the question for many years, what is a post-AGB star doing in a region where you have massive star formation, a very young star formation, right? And now with ALMA, it has been discovered that not only the SIO and the SIO are unique for being a massive star forming region, but they have found these kind of molecules like this aluminum oxide and this salt, the sodium chloride, the sodium chloride and the potassium chloride, which also is, you don't see that, now there are some researchers to look at in other star forming regions, but you don't see that in star formation, okay? So they are unique molecules that are very distinctive and unique with respect to the standard high mass star forming regions. And for example, the presence of aluminium gives you some hint. Aluminium, usually in the interstellar medium, is locked as most, I mean, all of the heavy metals are locked, like silicon, iron, aluminium, are locked in the dust particles. So in order to put it in the gas phase, it has to be like a very strong energetic event to release these heavy metals from the dust particles. So like an explosion, a very violent explosion. Otherwise, you don't see them, right? So this is an indication, all these molecules, there has been a strong dust sputtering, and that can only be produced by a violent phenomenon. Okay? And finally, the sixth evidence, and this is a work, that's a work we published recently, is from the magnetic field observations. Okay, this was initially a part of the extended capabilities of polarization with ALMA. We were part of a team that tried to extend the polarization capabilities for ALMA, and one of them 3 years ago was okay. Until 3 years ago, all polarization observations could be only done on a single pointing. Mosaicing was not allowed in polarization mode. So we wanted to test the capability of doing mosaicings in full polarization mode, to see if the instrumental polarization can be well removed when you do a mosaicing observations. So we selected Orion for this because the dust emission is very bright, so you can detect polarization very easily, and it's very extended. So you need a really mosaic to really sample well the dust emission. So in this image, you have like a 45 pointings. By the way, we found that the instrumental polarization can be well removed even in the mosaicing mode. So this is another technical paper that came out. Okay, but in the scientific paper we focus on because we have polarization from the dust emission. Let's check which is the magnetic field orientation. We know that in the Orion cloud, the magnetic field at large scale is more or less perpendicular to the dense filaments. Okay, and at the scales of 1 parsec, you see kind of the magnetic field being bended toward the center, like in a hourglass, and this is because the filament probably is contracting toward toward the center. Okay, and this is what we see when you go. And this is the Orion Nebula. This is the center. This is the ellipsoid here is the origin of the explosion. When you have the interaction of the stars. This is far away, and you can see the magnetic field. These segments are trace you the magnetic field. You can see the magnetic field is more or less perpendicular to the filament interstellar structure, and this is in agreement with the large-scale magnetic field. But when you go inside, you see kind of a more messy, perturbed magnetic field. And let's go now to a zoom in of the region. So this is a zoom in of the central region. The ellipsoid is where we think the dynamical interaction, the dynamic and explosive interaction between the massive stars are located. You can see here the dust emission from one of the three sources, source BN. The contours is the dust emission. So basically is the give you information of the column density of the gas. And the segments is the magnetic field direction, okay? And this is red lines that are centered in the explosion position. Is just to help you visualize the magnetic field. You can see regions like here. Let me just go again here. If you select here, you can see here the magnetic field has a radial behavior pointing toward the center. The same in this structure. The same with some here. You can see here the same. Magnetic field being oriented toward the center. Here, the same, okay? Even here, the same, okay? So we see kind of a radial magnetic field, especially you can see in all these is regions, are regions where the dust continuum is not very strong, okay? So you have more diffuse, less column density of the gas and dust, okay? When you go to the very dense regions, okay, like here, the magnetic field doesn't look as perturbed. That's because probably the self-gravity of the core doesn't allow the magnetic field to be more distorted by the explosion. Okay. Let's clear here. So I hope I can convince you that here, especially in the more diffuse parts, we see a magnetic field that is radial, also pointing toward the origin of the center. So that's also another signpost that this magnetic field has been perturbed by the explosion. Okay. So now let's go to the next slide. Now, on the left side, what we show here is the magnetic field from the dust polarization, and in color scale is the fingers, the CO fingers from ALM observations. This is the redshifted fingers, okay, that are radial. And you can see there is a correlation between the CO fingers and the magnetic field. Of course, the fingers are tracing very high velocity gas being pushed away from the center. So this is even more diffuse gas. So the dust only picks up the regions that are denser. That's what you see at these. They are, in fact, they're a bit anti-correlated, but in the same direction. Okay. And the circle here, it marks approximately the region where we see the magnetic field being perturbed. So in a scale, we see that the magnetic field is being perturbed up to 5,000 AUs. Okay, the outflow extends much farther away, like up to, I think it's 0.05 or 0.1 parsecs. But the magnetic field is only perturbed up to 5,000 AUs. And because we know the time scale, which is 500 years, that means that the shock propagation that is affecting the magnetic field is propagating at a velocity of about 50 kilometers per second. On the right side here, you see from the distance of the explosion center, the difference. This is the difference between the observed position of the magnetic field, which is, remember, this is projected on the plane of the sky, with respect to the radial value you will expect if it's completely radial. And you can see up to 12 arcsecond, which is the 5,000 AU. You see that at least a significant part of the magnetic field has a radial component. Okay. And this is now overlap of the magnetic field and the molecular hydrogen fingers. Okay, this is the region perturbed by the magnetic field. This is the shock traveling at 50 kilometers per second. That coincides relatively well with the chemical distortion of the chemical of the molecular line, the molecular gas effects of perturbation. Also, you see at this scale, you see also the molecular gas being perturbed by the explosion. Okay. Okay, so now just finish the sixth evidence. I hope now you can believe that 500 years ago, so that's in the 1600 century, there was a big explosion in Orion. It would be nice to look at the historical records, if there is any from, I don't know, from the Chinese, from the Europeans, from, I don't know, from the Americas, to see if there is any evidence of this explosion from the in the optical. The thing is, this is everything. This even in the alpha, this near infrared. So this is at long wavelengths that our eyes cannot see. So it would be nice to see if this explosion could be seen in the optical, and there is any records, historical records. Okay. So as I say, I hope that you believe that I convince you that there was a dynamical interaction of at least 3 massive stars, probably with more stars being involved, because some of the stars are formed in multiple systems, and you have these 3 massive star runaways because of this interaction. This produced a huge explosion, and we are seeing now the consequences, and therefore the Orion is a really very interesting lab to study this kind of things. That means if that happened in Orion, that's probably happened in other massive star-forming regions, because of the basically you have the clusters are the high mass stars are forming clusters. So this so I'm going to show you a simulation. This hydrodynamical simulation includes radiation by Matthew Bates. Of course, it doesn't have all the physics, but as a first image of what happens, you can see when you form a cluster, right, in a very dense and a massive environment. Okay, you form a cluster of stars, and because of the gravitational potential, you basically make the stars to go to the center of the gravitational potential, and then it is possible to produce this kind of interaction between the massive cores. Okay, and you can see here some stars being some runaway stars because of this interaction. Okay, so that's probably what happened. Okay, so another question is, but what about the fingers? This explains the dynamical interaction, but can you produce this kind of very complex fingers network of fingers? So this is a very cool video of an explosion. Here you have, that's what you see, right? I guess everybody now can relate this with Orion. And this is just an spherical amount of particles when you have an explosion in the center. Okay, this is the dispersal of solid particles. Okay, and this is what happens. Okay, and you see an explosion when you have small particles will produce this kind of fingers. So this is expected in the nature just from this kind of experiments. Now this video is a bit long. I apologize for that, because they show how these fingers produce fingers in the explosion change on the conditions of the material that is surrounding the explosive. Okay, so in this case it's water, liquid water. Of course, you see the fingers are much more narrower and they disperse soon. This is probably the previous experiment is more realistic, which may happen with Orion, because in Orion you have basically gas, very dense gas, and you have dust particles. So you have the ingredients. You don't have liquid water, right? But and this is a water-bed glass particles. And so you see again the filaments going on. And in this case, you can see it's completely spherical, these fingers. Okay, now you can see the 3 different composition of materials. You can see the different behavior. So you can see the one on the bottom left is the one that looks more like Orion, right? Is the glass particles. Okay. which is very interesting to see that in nature can really produce this kind of explosions. Okay, and here the next step is okay, and this is also what happens instead of being a spherical, like a spherical. You have like a cylindrical shape. You put the explosion in the center of the cylinder, and now we're going to see how the explosion happens. Okay, this is also very interesting. Look at the left. It's probably more related. You see again the fingers, but you see also kind of a spherical shell produced. And this is more closer what we see also in the in Orion, right? And this is because this cylindrical shape you can think about because when before the dynamical interaction of this massive star, you were surrounded by a filament that can be think of a cylinder of very very dense gas, right? So the explosion doesn't happen in a spherical, asymmetric geometry, but more in a cylinder geometry. And with that, I just conclude. This is from Zapata. I want to thank Luis Zapata because he provided me several of the slides I presented today that helped me to prepare this talk. So as a bottom line, well, 500 years ago, there was a huge explosion with an energy of the order of 10 to the 48x due to the dynamical violent interaction of at least 3 massive stars and probably more stars involved in the dynamical interaction. And this is, therefore, this is a unique laboratory to study this kind of those effects. And this is probably not unique in Orion. This may happen from time to time in other star forming regions. So now the people in Mexico, they are looking for other massive regions where they may find you may see these kind of effects. And I think they have found a couple of them already in the regions. So thank you very much for your attention. That's it.
Thank Josep Miquel for this nice talk. And indeed, from the point of view of completely non-expert, the cool videos of the explosions really looked like the observations of the,
when I saw that,
these fingers, right?
Yeah. Yeah, I mean, the astronomers, we're looking for 30 years thinking about what's going on with this kind of very complex network of fingers, and they were not clear what happens. And then you have these people, physics, doing a small experiment, easy to do, and they show you, well, here you can produce the fingers, right, in an easy way.
Okay, then is there any question? So if any of you has a question, please go ahead and unmute yourself and ask the question.
I had a question. So Josep Miquel, can you hear me?
Hi, Pablo. Yeah.
Yeah, so my question is obviously very naive because I don't know anything about this topic. But so I was wondering from your presentation whether this sort of explosions are something to be expected more commonly, let's say, within the Milky Way in other molecular clouds, and whether this might explain to some extent the star formation rate of a galaxy like ours. No? So whether this is a mechanism that can account for that to some extent.
Well, yeah, of course. I mean, if you see in astronomy, when you see one of these things, you expect that this is not unique. I mean, it's unique because from the statistical point of view of what we knew so far, there was nothing like that, right? But you expect that this happens because massive star forms in clusters, and this is like a 4,000 young star being formed. But we know in the galaxy we have other massive regions where the number of stars being formed is even larger by a factor of few. So this may happen too, right? The question is how often it happens. Huh? In fact, there is now a team trying to look for evidence. Of course, the problem is that these massive stars will be at larger distances, so it will be more difficult to find. But there has been at least one or two other massive star forming regions where they see this kind of finger-like kind of isotropical that may be explained by this kind of dynamical interaction of the stars. And of course, because this is a lot of energy involved, and this is basically outflow going out, that's going to disperse on what the molecular gas around that, right? So they may have an effect on the star formation rate, right? It may trigger, but it may disrupt, right? That may explain why the star formation rate in the galaxy is lower than what is expected with the number of gas you have, the molecular gas in the galaxy, right? But this is very localized and it happens from time to time. So it may help a little bit, but not from the overall point of view. That's mine.
And is it,
Yes.
sorry to ask, is it possible to estimate the rate at which this happens, let's say in a system like the Milky Way with some simulations, or this is very tough to simulate?
Well, I mean, there are people do, I mean, here in Barcelona, we have Paolo Paduan doing these simulations. Yes, I guess, I don't know if the people doing simulations has already tried to answer this question, but I guess, yeah, that would be interesting to see when you form a GMC and you want to simulate the formation of the full cluster, how often this happens, right?
Yeah, thank you.
With respect to the time scale of formation of the cloud.
Right.
More questions? Okay, then if there are no more questions, thanks Josep Miquel again. And thank you also for this last minute presentation, filling the hole that we had. Thank you very much.
Okay.
Thank you.
Thank you. Bye.
Bye-bye.
See you all next week. Bye-bye.
Bye.
Thank you.
Bye.
Bye.
See you.
Thank you. Bye bye.
Thank you. Bye bye.